Good day, everyone. Welcome to another lecture on this lecture series related to the machine learning. And in this particular lecture, we will be discussing about the generalization, or we can say the performance of a model on unknown data. What I mean to say, so in our previous lectures, what we did, we find out a hypothesis function, that particular function that maps, or we can say that captures the input output relationship, and how we are able to find the best hypothesis function. For finding the best hypothesis function, we have a cost, and we optimized this cost. Okay, cost here means that we optimized the mean square error. But you may have find out that this mean square error that we are optimizing, basically we are reducing the errors made on training data, or we can say training data is also our known data, that is known to us. We know what is the input and what is the output. In other words, I can say we are minimizing the loss on training data. But in actual case, when we are deploying our machine learning model, so we have found out H, hypothesis function, and now we are deploying this hypothesis function. And deploying it means now it sees an unknown data. Unknown data means the data that was not available in the training data set. It sees the unknown data, unknown input, and it has to make the predictions, or we can say it has to give us the predicted output, what it predicts this hypothesis function. So we have to see, if we find out a hypothesis function, whether this particular hypothesis function is generalizing on an unknown data or not. If it is not generalizing on an unknown data, we will say that it is of no use, because we need a machine learning model only to predict the unknown behavior. And it we developed this hypothesis function by reducing the errors made on the training data, but now we have to find out whether it is working properly on the unknown input or not. So this unknown input, it is also called validation data, or we can also say it test data. So basically that these two, validation and test, they have their own meanings, but here in generalization we will say validation and test as same. Okay, but in our subsequent lectures we will discuss what is a validation data and what is a test data. So after making a hypothesis function, we have to evaluate this hypothesis function, evaluate on unknown data. And this unknown data is also called validation data or test data. And then we have to find the error of this hypothesis function on this validation data or test data, which is also called, we have to find the validation error. And we will say that this particular model is best, or we can say it is good, or we can say it is generalizing to the unknown data if this validation error is very less, or we can say if the test error is less. Okay, we want that this test error should be very less. Fine. So this comes under the generalization concept. So if our model that we have created, it is generalizing very well to the unknown data, that means the validation error or the test error is very less, then we will say that this particular model is a generalized model, or we can say it will predict the output of an unknown data as well. However, this is not always the case. So there is a possibility. So there are two possibilities. What are the possibilities? The first possibility is that our model, this particular model, this model was not able to capture the relationship in the training data. So even in the training data, this model was not able to capture the relationship. So we can also say that in this case, training error will be very high. So in which scenario our model won't be able to capture the relationship in the training data? So the reason, or I can say this scenario will happen when our assumption about the hypothesis function was incorrect. What I mean to say, let me write it on a new page. So I am saying here, so let's suppose my data was like this, my training data was like this. So let me make it here. So my training data was like this. So these are different data points, and I will assume that I will have a linear hypothesis function. So you can see that this particular linear hypothesis function won't be able to capture the data points, or we can say the input output relationship in the data set, even in the training data set. Why? Because the training data set is saying that the input output relationship is not linear, but we are assuming that the relationship is linear. So in this case, our hypothesis model that we have created, the training error will be very high. So that is what I am saying here. I am saying that for making an error, there are two possibilities. That model was not able to capture the relationship in the training data, or we can say the training error is very high. So even in this particular model, in this particular scenario where our model was not able to capture the input output relationship, now even if it sees an unknown data, it won't be able to generalize on an unknown data as well, because unknown data will also follow the same pattern that is there in the input data. And we are saying that it is not able to, this curve won't be able to capture the input output relation in the training data, so it won't be able to capture this unknown data as well, or we can say the error. So this is the error, the difference of these points from the actual line. So this particular error will also be high. So in this particular scenario, both the training error as well as the test error, or we can say validation error, will also be very high. Okay, and in this particular scenario, we will say that our model, the machine learning model that we have chosen, it underfits. This is also called underfitting. So what is the underfitting? Underfitting means that when our model is not able to capture the relationship in the input and output data in the test set. Okay, so and why it is why this scenario happens? It happens when our assumptions about the hypothesis function is not the same as the relationship in the training data set. Or we can say the function that we are assuming is not the function of data generation, test data generation, because the data is generated by some particular function and we want to capture that function, but we are assuming a different relationship. So in that scenario our model won't be able to capture the relationship. So you can see how I can solve the problem of underfitting here. So you can put some pressure on your mind and you can see that instead of using a linear function, we can easily see that the hypothesis function should be chosen as non-linear. So we will use a hypothesis, a new assumption, that is we will use a non-linear function. That means we will use a quadratic function because the behavior here is quadratic. So we can do that by using polynomial regression. So our quadratic model will be best suited in this particular scenario. And our quadratic model won't overfit. Why it won't underfit? It won't underfit because it will be able to capture the relationship. And we were making a bad assumption. We were saying a linear hypothesis. So it was our bias towards the linear model. Okay, so we were more biased towards the linear model, that it will be a linear model, but the actual relationship was not linear and it will result in underfitting. So here I have shown a quadratic data. So let's say the data was like this. So it was more we can say random. And how you can capture a relationship? You need a curve like this, or this can also be captured using a high degree polynomial. Okay, this type of relationship. So if we have a more random relationship, you have to assume a high degree polynomial for a hypothesis. Okay, so you have to understand that high degree polynomials will capture almost all the data points in the data set. High degree polynomials. So here first we were assuming linear. Linear was very simple. So this simple was not able to capture the complex relationship. But when we are making our model complex, that means very high degree polynomial. So that will be a complex model. So it will be able to capture almost all the data points in the data set. So that means in this scenario, training error will be very less. Okay, but the main problem with this particular scenario is that it won't be able to generalize to unknown data. High degree, or we can say more complex models won't be able to generalize to unknown data. For example, it was trying to fit every point in the test data, in the training data, sorry. Now, if there is some unknown data, so first when we created a model, it was trying to fit the all the points in the training data. Now it find out some unknown data and it won't be able to generalize for this unknown data as well. So this is the problem with high degree polynomials, this kind of models. So they won't generalize to unknown data. So this is the second scenario. So here the first scenario was underfitting. So we understood the underfitting and the reason. The second scenario is that, so the second scenario is our model captures the training data almost completely. So that means this model tries to fit all the data points in the training data set. So this will result in very less training error. So the training error will be very less. But this model, if it is more complex, so it will be a more complex model. This model won't generalize to unknown data. So if it is not generalizing to unknown data, that means our validation error will be very high. Okay. So our aim is, what is our aim? Aim is to have a model which has less training error and less validation error. Less training error and less validation error. We showed that in the first scenario, if the model was very simple model, for example, a linear model, simple model may result in high training error, or we can say simple model won't be able to fit all the data in all the scenarios. So it will result in underfitting. Okay. And now if we are making the model complex, okay, why we were making the model complex? So that it won't overfit, it won't underfit. Okay. But our model that tries to capture all the data in the training data set will have less training error, but in for this particular model it may result in generalization issue, or we can say it won't generalize to the new data, unknown data. So sometimes it may, sometimes it may not. So this particular problem is also called overfitting. So we want to choose a model that has less training error and less validation error, or we can say the model that neither underfits nor overfits. We want this particular model. Okay, we will see how we can design a model that neither underfits nor overfits. We will see that when we will discuss regularization. How we can choose a model so that we can avoid both overfitting and underfitting. Okay, you can also see that, see, if I have a simple model, it has the problem of underfitting. If I have a complex model, it has the problem of overfitting. Underfitting was because of bad assumption about hypothesis function, and overfitting is because of, it is because our model is trying to fit all the data in the training data. Okay, training data set. Now if there is some variation in the training data set, it will result in errors. Okay, so this particular data is sensitive to small data variations. Okay, so this particular models are also called high bias models. I will show what is this bias, and these models are high variance models. So first we will need to understand what is the meaning of bias and what is the meaning of variance. Then we will see why it is called a high bias model and why this one is called a high variance model. And before discussing this bias and variance, you have to understand, if I choose a model, so let's suppose I have choose a model. So there is a model. How can I say whether this model is overfitting, underfitting, or overfitting? how can we answer this? Whether a model is overfitting or underfitting. We can answer this by understanding the learning curves. What that means is I will make you understand what are these learning curves. So first we will discuss learning curves, then we will see what is bias and what is variance. Okay. So let us say we have a model and now we have to check whether it is underfitting or overfitting. How will we do that? As I said, using learning curves. So what is the learning curve? So I will make a graph here for this particular model. So I have a graph. So on this side we have the error, and on this side we have the training data. Okay, so we have this model and we have to check model M whether it is overfitting, underfitting or overfitting. Let's assume this model is underfitting. Then if this model is underfitting, we will plot some curves. So what curves? We will first find the errors of this model, training error and both validation error. Okay, now let's see. When the training data is small, so let's suppose only 1 or 2 points in the training data. So this is the training data. We are increasing the size of training data, or we can say we are increasing the number of examples in the training data. So when the number of training examples are small, since we are saying the model is underfitting, so it will be a simple model. Let's suppose a simple line. Okay, a linear model is simple model. So for example, you can see that if I have a simple model like this, if there are only 2 points, it can easily capture these 2 points. Okay, even the linear model. So for small number of data points, the training error is very less for simple model. But if I am increasing the number of data points, so for example, some data point, it won't be able to capture these data points. Small number of data points it will capture. So for small training data set, training error will be less. But when I increase the size of training data, the training error will increase. And this will only be in the case of simple model, or we can say when the model overfits. So here I can plot the graph like this. Initially training error is very less. Okay, so initially training error is less, then it is initially from the start from 0, but eventually it will go on increasing like this, and after some time it will neither increase nor decrease, it saturates. Okay, the training error saturates. Fine. So but you have to understand that this particular graph is for when model underfits. Now for the same model, if we see the validation error, so this was our training error on training data, and the validation error, okay, the validation error, initially validation error will also be very high. Why validation error will be high initially? Because initially we are having a small training data, and small training data won't be able to capture the entire relationship on the unknown data as well. So initially training error will be validation error will be very high. Okay, and it will go on decreasing with increase in size of training data. So validation error will be like this, but it will also saturate after some time. So this is our validation error. So this was training error and this is validation error. You will see that both the training error and validation are very high, and the model is underfitting, sorry. And you can see that for large data, training data, so there is this these two curves, training error and validation error, they are close to each other. And also in the underfitted model, you will see one important thing, that by further increasing the training data, there won't be any change in the error. So that means by increasing the data, you won't be able to learn more. Usually in machine learning, we say that having more data means we will capture more information. But if the assumptions that we made are not correct, then even after increasing the training data, we won't be able to get more information. So this is the learning curve for a model that underfits. Now let's see how does learning curve behaves in case of a model that overfits. So what is an overfitted model? Overfitted model means the model that tries to fit all points in training data. Okay, you can easily see that for this particular model, the training error will be less than the underfitted model as well. So let me make the curve for this model that underfits, that overfits. So in that particular scenario, the error will remain 0 for most of the time, and it will increase, but it will be very, very less training error. But we already know that for the model that overfits, the validation error is very high. So initially it will be very high. Okay, and it will go on decreasing, but after some time it will remain constant. Validation error. This is for a model that overfits. So this is training data on this side, and this is error on this side. So you can see that both these curves are looking similar, but the difference is that the model that underfits, there is a very small distance between the validation error and the training error. But the model that overfits, there is a very large difference between the training error and the validation error. Why? Because in a model that overfits, it tries to reduce the training error as much as possible, but validation error will be very high. Why? Because it is not generalizing to unknown data. So there will be a very high difference between the validation error and the training error. Okay, so if we have to find out, so we got 1 point from here. So if we have a model, so let's say we have a model. Okay, and for this model I have to answer whether this model underfits or overfits. And how can I answer this? I will do one thing. I will find the training error and validation error on large training data set and validation set, and I will see if training error is very, very, very less than validation error, then this model overfits. And if training error is close to the validation error, then this model underfits. But you have to also keep in mind that this error should be very, very large. Then only we will say that it underfits. But if the error is very less, both training error and validation error are very less, then we will say that it is a good model. Okay, but if error is very large and both training error and validation error are almost same, not almost, but we can say that they are close to each other, then we will say the model underfits. Otherwise we will say the model overfits. Okay, this was all about the training, or we can say about the learning curves. Now we have one important thing that we have to understand. One important graph is here. So I will make this graph that you have to keep in mind. What this graph suggests is, this particular graph, it is saying that if we plot model complexity and error. So this is our error. Okay, now first let's take the training error. So for a training error, if I am plotting this graph for a training error, so the model which is very simple, so here we have simple model and here we have complex models. So we are going from simple to complex models. If our model is simple, its training error will be very high. Okay, so its training error will be high. And if we go to complex models, from simple to complex, the training error will decrease. Okay, so we already discussed it. So it is like this. So this is about the training error. So what I mean to say, that training error is decreasing with model complexity. Okay, such a model where this training error is happening like this, you already know that this kind of model may overfit or underfit. We will discuss that in couple of minutes. Now let's take, this was about the training error, let's take the validation error. So for a simple model, validation error will be, what will be the validation error for simple model? The validation error for simple model will be less, and with increasing the complexity, validation error will increase. Okay, so it will be like this. So this is validation error curve and this is training error. You can see that in this particular scenario, here in this particular section, here both the training error, or we can say the training error is very high, validation error is less. We usually say that these models underfit. And here training error is very less, but validation error is very high, and these models overfit. So we want a model in this particular domain, a model where both the validation error and the training error are very less. Okay, these are our, we can say, good models. Fine. So this was about the underfitting and overfitting. Now let's continue the discussion about this thing again. So what we said, that we have a model M, okay, and there is a possibility that this model may underfit or overfit. And we already discussed how we can find out whether the model is underfitting or overfitting. Now there is one important thing here, is that we have to understand two important terms. One is the bias, another is variance, or we can say the errors. Errors in machine learning model are divided in two types. One are the reducible errors. Reducible means which can be reduced, and another errors are irreducible, which is difficult to reduce. And these reducible errors are of two types. One is called bias, another is called variance. And irreducible error, it is mainly because of noise. So since we don't care about the irreducible errors, we will only check about the reducible, because these errors can be changed. Okay, we can vary or we can increase or decrease these errors. Bias, this particular error, it is basically the difference between actual value and predicted value. So if our predicted value is h of x and our actual is y, so this error is called a bias. Okay, and variance, this particular is also an error, this particular quantity. But what kind of error? Basically this error amounts to data variations. What I mean to say here, I will discuss this in couple of minutes, this variance. Okay, fine. Let's see how bias and variance can be related and how we can measure this variance. What is this variance? So basically our actual loss, what was our loss? Loss was j theta. We will show that this particular j theta or this particular error, as we said that there are only two types of errors, bias and variance. We will say that this error is a combination of bias and variance. Okay, let's derive it, how it is a combination of bias and variance. Okay, so before deriving this you have to keep in mind, so x, we already know this from mathematics, from the probability, expectation of x minus expectation of x whole square. Okay, so this can also be written as, this is expectation of x minus mu whole square. Okay, mu is the mean of x. The mean of x is given by expectation of x. We are going to discuss this in couple of lectures, after 1 or 2 lectures, when we discuss about the probability. But one thing you have to keep in mind, that this equation is equal to expectation of x whole square minus, sorry, this is equal to expectation of x square minus expectation of x whole square. So for understanding this, you have to keep in mind, what is the expectation of x? Expectation of x is also called the average of x, average value of x. Okay, so we are saying expectation of x minus mu square, this is the mean or average of x ka whole square, is equal to expectation of x square minus expectation of x whole square. And this can be written as expectation of x square is equal to expectation of x whole square plus expectation of x minus expectation of x square. Okay, this is the equation that you have to keep in mind. So what is the equation? Let me write it here. So I am saying, so we will use this equation in our derivation. So the equation is, let me write on a different paper here. Yes, so because we will be using this equation repeatedly, so expectation of x square is equal to expectation of x whole square plus expectation of x minus expectation of x square. So this particular equation we will be using. So how we will use it, I will show it later. Okay, so but you have to keep in mind. So what I am saying, what is our aim? Our aim is to find out how we can express our j theta, how we can express this j theta as a combination of bias and variance. Okay, we already know what is the bias. Bias is like this, y minus h theta x. So the difference between the actual and the predicted value. So this is bias. Variance, basically variance, we are saying it is the variation of the chosen model from the variation of the chosen model from the best model. Okay, so how many models are possible? So there are n number of models possible. Okay, so there are many models possible. So let's represent those by s. So s can be anything, 1 2 3, and the best model is ha, where ha is the average of all these models, or we can write ha is the expected value of hs. All these models, average of all these models is the best model. And I can find out if I have chosen a model, some model, and now I have to find out it is variation from the best model, and that particular variation, how we can find out the variation? We can do, so basically it will be like this: variation is h chosen model minus hs whole square. This is called the variation. Okay, we will discuss this in this again. If you are not able to understand here, I will show it here. So let's write it. So what is our j theta? What is j theta? We already know that j theta is equal to expected value of y minus h s x whole square. This is our j theta. So have we discussed anywhere this j theta is like this? No, but I will show you how this is like this. So what was our j theta? So j theta was mean square error. So mean square error, we used to write it like this: h of, you can write h first or y first, it is one and the same thing. Why one and the same thing? Because square is here. So this is the mean, and mean can also be written as expected value of y minus h theta x whole square. So expected value of this quantity, or we can say the average of this quantity. So that is why I am writing that this particular error is equal to expected value of y minus h of hs, or you can write h theta. It is one and the same thing, hs of x whole square. Okay, so what I am saying, that I am choosing a model. So there are different possible models, and among them, if I choose one of the model, then its error will be like this. Okay, or for simplicity, or we can say the uniformity, you can write theta. So this is our error, or we can say the mean square error, the error that we have to reduce to find the optimal set of parameters. Let's assume, or we can say, let's have an hypothetical, it is a hypothetical situation. Let's have an infinite number of training data sets. We have infinite number of training data sets. Okay, so we have a training set t1, we have a training data set t2, we have infinite training data sets. On this particular model, we are having a model hs1x. On this training data, we are having a model hs2x dash dash dash. On this training data, we are having a model h infinite x. So for each training data set, we are having a different model. Okay, this is one model, this is another model, this is another model. So we have infinite models. Okay, and from these models, the best model will be the average of these models. So it will be the, I will write average model. Average model will be the expectation of these models. SI. So SI can be anything. 1, 2, 3, 4. Average of all these models is our best model. We will also say that if all these models are almost same, so that means these models are very less sensitive to the data variations, to one to variation in from one training data set to another training data set. If there is no difference between these models, no significant difference, then we will say that they are very less sensitive to the training data variations, or we can say that these models will generalize very well. Or in other words, these models won't under overfit, because when they are generalizing very well, so that means these are not overfitting. In other words, we will say the variation of these models from the best model, or we can say from the average model, will be less. And how we write the variation will be expected value of, so let's suppose if I have to find the variation of x, the variation of x is written as variance of x minus mu whole square. And if I have to find the variation of any of the model, it will be the expectation of x. So x is changing, so here our models are changing, it will be hs x minus mu. So mu will be the average. What is the average? Expected of these models, or I can write h average whole square. This should be less, and this is called variance. So what is the variance? You should understand the term. What is the variance? Variance is the variation of these models from the best model. If the variation is very less, that means they are very less sensitive to the change in data. So that means they are generalizing very well. And when they are generalizing very well, that means they won't overfit. So if variance is less, that means there is no overfitting. However, if variance is high, very high, so that means these models vary very much from each other. So that means they are very sensitive to the training data. Okay, so that indicates that these models overfit. So that is why when I have written here, as I have written that this model is called a high variance model, overfitting model, you now understood why it is called a high variance model. And this is high bias because it has very high training errors. Or bias was the error between the actual and predicted. So since the actual and predicted, it is a simple model, so there will be very high bias, very high these errors, and it is called a high variance. So we understood why it is called a high bias model and why it is called a high variance model. Okay, now let's come back to our actual equation. The actual equation was, so our actual error, so the total error was j of theta is equal to, so it is expectation of, as I have written, y minus h theta x whole square. Okay, or I can write it like this. This is equal to, let's say this is our x, let's rename it with r. What is r? R is y minus h theta x. So this is r. Okay, so this is also expectation of r square. And expectation of r square, as I have shown here, expectation of x square is like this. So it will be expectation of r whole square plus expectation of R minus expectation of R whole square. So I am using this particular equation here. So now let's give the values back. It will be equal to expectation of R. What is R? Y minus h theta x whole square plus expectation of, what is R? R is y minus h of theta x. So h of theta, or we can write h of s, because now we are choosing infinite number of models. Okay, so let me write h of s. So these are all h of s. Okay, minus expectation of R. So what is R? Y minus h of s x and its square. This will be equal to, you can see expectation, or we can say the average of these errors. What are these errors? This is the actual minus predicted. It is also called a bias. So the average of these will be a bias. So it is bias square plus, okay, expectation of, so this is y minus h s of x. So it will be expectation of y minus this will first expectation of y and expectation of this, because we know expectation of a plus b will be equal to expectation of a plus expectation of b. And since y is a constant, and for constant expectation is a, okay, so it will be minus y, minus into minus will be plus expectation of h s of x whole square, and it will be equal to bias square plus expectation of, so this y and this y will cancel. It will be expectation of, let's first write this. So it is expectation of average of these infinite models. As we said, the average of these infinite models is the best model. Okay, so we will write it as the average model minus h s of x whole square is equal to bias square plus, now let me write average of, or this particular quantity, what it is called. So as I have shown you here, so this particular quantity hsx, so hsx minus h of a, minus h of a, or you can also write it h of a minus hs of x whole square, because of this square you can write either this first or this first. So this is called variance, okay, plus variance. So you can see that our error is equal to bias square plus variance. So we have to decrease the bias and we have to decrease the variance as well. But from the equation also you can see, if we are increasing bias, decreasing bias, variance may increase. And if we are increasing bias, variance will decrease. So there is a trade-off. So this is also called a bias variance trade-off. We have to choose the optimal value such that both the bias and the variance, they are within some particular limits. Okay, so this was all about the generalization, how we can do the generalization. So this is our j theta. Now our aim is to design a model. How we can design a model that has low bias and low variance, and that will be the discussion of our next lecture. And in that lecture we will discuss about the regularization. So in regularization we will try to make low bias and low variance models. Okay, so before wrapping up this particular lecture, let me recap two terms here. Two or three terms. One is underfitting. So what is underfitting? Underfitting means simple model, as a result giving high training errors. And overfitting is the complex model, high validation errors, or we can say sensitive to data variations. These models are called high bias models. Why high bias models? Because the errors are very high, bias is very high. Okay, and these are called high variance models. Why high variance? Because the variations of the models in comparison to the best model are very high. Okay, and our aim is to have low bias and low variance. That is done using regularization. And we are also understood that our j theta is equal to bias square plus variance. So our error has both the parts, the bias part and the variance part. So let me stop this particular video here. Let's meet in the next lecture where we will be discussing about the regularization. Till then, goodbye.